Welcome back to Calculus, everybody. It's section 2.3, and it's time for rules for differentiation. In this section, we're going to talk about a positive integer power rule, multiples, sums, and differences of derivatives. We're going to talk about the product and quotient rules. We're going to talk about negative integer powers of x, and finally end with second and higher order derivatives. But this video starts with positive integer powers, multiples, sums, and differences. We have some new theorems in this section. We're going to talk about the derivative of a constant function, a power rule for positive integer powers of x, a constant multiple rule, and a sum and difference rule. And we'll spend a little bit of time with a power rule because it's just the most important rule we have seen so far in our study of calculus. So we begin like this. The first rule of differentiation is that the derivative of every constant function is the zero function. And here's the rule highlighted in violet. If f is a function with the constant value c, then df dx, or the derivative with respect to x of that constant function, is zero all the time. And what that means is if we have a function, say for instance, f of x is equal to 5, well then f prime of x is equal to 0. If we have a function such as say y equals negative 475, well then we have dy dx is equal to 0. Any constant function or number, just a number on its own, the derivative is always 0. Now I've got some white space up here because I'd like to develop the next rule. I want to talk about first the derivative of x squared, and then we're going to move over to the derivative of x cubed and see how those look. So we know the derivative is found this way. It is a limit as h approaches 0 of f of x plus h minus f of x all over h. So in the case of x squared, we're looking at x plus h, quantity squared, minus the function itself, minus x squared, all over h. And so this becomes, after expansion, the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. And after that, we take a look again and see that the x squared minus x squared becomes 0. We can circle and cross those out. And then the remaining two factors both share an h, and so we look at the limit as h approaches 0 here. Again, we factor out an h. We have left over 2x plus an h, and this is over h, and then we have an h be canceled. And finally, we are left with a limit as h approaches 0 of 2x plus h, and we can go by direct substitution. We have 2x plus 0 finally for a derivative of 2x. So the derivative of x squared is 2x, and that's a process that took us 6 lines of work to reach the final answer. Now let's do the same thing with the derivative of x cubed, d dx of x to the third power. So this is, again, a limit as h approaches 0 of, this time it's x plus h quantity cubed minus the function x cubed, and this is all over h as normal. In our next line of work, as you suspect, we're going to expand. So we have x cubed plus a 3x squared h plus a 3x h squared plus an h cubed minus the x cubed. This is all over h. And just like in the derivative of x squared, we see the x cubed terms cancel. And then we see the remaining three terms all share a factor of h. So our next line of work, we will spend factoring out that h. So let's do that here. Take out an h. That leaves left 3x squared plus 3xh plus h squared, and that's all over h. And just like in the previous question, the h's will cancel, and we are left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared. And as h becomes 0, this is 3x squared plus 3x times a 0 plus a 0 squared for a final answer of 3x x squared. And this process was a little bit longer than the process for x squared because the expansion of x plus h cubed took one more term. And you can imagine that as we begin to move up the hierarchy of degree into a derivative of x to the fourth, x to the fifth, x to the sixth, and so on, that this process becomes even more and more complicated with that expansion of the x plus h. So as we do in math, a lot of times we pause for a second and see, are there patterns to pick up on? Is there anything that is like a repeated clue that we can maybe use to develop another way to work about a longer type of question such as this? And you may see it already. To go from the derivative of x squared to 2x, and to go from the derivative of x cubed to 3x squared, you may see that the coefficient of the derivative is the exponent of the original function. And the new exponent of the derivative is one less than the exponent of the question. And we can go through the process of x to the fourth and x to the fifth and show that works as we continue to increase the degree. So that means we have ourselves a rule, and it's called the power rule. This is a rule that we can use for differentiating polynomials. It says that if n is a positive integer, that the derivative of x to the n with respect to x is equal to n times x to the n minus 1. Essentially, what we do is bring the exponent of the term x to the n down to the front as a coefficient, and we decrease that exponent by 1. The power rule is written in words down here to differentiate x to the n. Multiply by n, subtract 1 from the exponent. For example, the derivatives of x squared, x cubed, and x to the fourth are 2x to the first, 3x squared, and 4x cubed respectively, which means if I asked you for the derivative of x to the 10th, you could tell that to me without going through the limit definition of derivative and expanding x plus h to the power of 10. This is just 10 to the front times x to the 9th. So let's move on. Here's another rule. It's called the constant multiple rule. It says if u is some differentiable function of x, so u just stands in place of some function, and c is a constant, then the derivative of the constant times u is equal to the constant times the derivative of that function. In other words, the constant just kind of comes along for the ride as a multiplier. So if we looked at, say, the derivative of 5x, we would have 5 times the derivative of x, which is 1, which is now 5. If we looked at the derivative of, say, 3x to the fourth, we would have the 3 as a constant coming along for the ride times the derivative of x to the fourth, which we now know is 4x cubed, for a final answer of 12x cubed. So any constant before a function as a multiplier is also a constant as a multiplier in the derivative. And we see down below, combined with the power rule, it enables us to find the derivative of any monomial very quickly. Here's an example. The derivative of 7x to the fourth is 7 times 4x cubed, which could be 28x to the third. Finally, a positive integer multiple of some. So just like with limits, the derivative of a sum of functions or the derivative of a product of functions is equal to the sum or product of the derivatives. So this means now we have the ability to find derivatives of all polynomials because polynomials are sums and differences of monomials. If we look at the derivative of, say, x to the third plus x squared, we know now this is the same as the derivative of x cubed plus the derivative of x squared, and that now with the power rule is 3x squared plus 2x. And we can differentiate polynomials so much faster than we could with the limit definition. So here's an example. Find dp dt, find the derivative of p with respect to t if p is equal to t cubed plus 6t squared minus 5/3 t plus 16. We can employ all of the rules that we learned previous to this slide and say that the derivative of p with respect to t. dp dt is equal to, first term, t cubed, that derivative by the power rule would be 3t squared. Then we use the sum rule and the constant multiple rule and say the derivative of 6t squared would be 6 times the derivative of t squared, which is 2t. Then we use the difference rule and the constant multiple rule and say this is minus 5/3 times the derivative of t, which by the power rule is 1. And finally, we use the derivative of a constant rule and say the derivative of 16 is 0. And we'll simplify that answer as 3t squared plus 12t minus 5/3 and have ourselves a result. Let's put this to use in a bit of a more conceptual question. Does the curve y equals x to the fourth minus 2x squared plus 2 have any horizontal tangents? And if so, where? A horizontal tangent, a tangent that is completely horizontal, we know is going to be a line with slope 0. And if the slope is 0, then guess what? The derivative dy dx is going to be equal to 0 at those places as well. So what we can do is find the derivative of this function, set it equal to 0, solve, and we will find any points of horizontal tangency. So now with the power rule, with the sum and difference rule, with the constant multiple rule, we can quickly say that dy dx, the derivative of y with respect to x, is the derivative of x to the fourth, 4x cubed, minus the derivative of 2x squared. We're going to move right into the answer. That's going to be minus of 4x because 2 is the constant multiple. Derivative of x squared is 2x, so 2 times 2x is 4x. And then the derivative of 2 is 0, and we'll leave that alone. This is dy dx, the derivative. We know that the derivative of a horizontal tangent will be 0, and now we can solve. Well, 4x cubed minus 4x is a function that has a common factor of 4x, so we can pull that out and have left over x squared minus 1. This is still equal to 0. X squared minus 1 is a difference of 2 squares, so that also factors into x minus 1 and x plus 1. So we have our derivative fully factored, and we can set each of those factors equal to 0. For x is equal to 0, x minus 1 is equal to 0, x plus 1 is equal to 0, and have the results x is equal to 0, x is equal to 1, and x is equal to negative 1, so that all the points with these x values, there are horizontal tangents. Those points are 0, comma, well, let's see, what do we get when we plug 0 into this function? That'd be 0 minus 0 plus 2, so 2. We have the point 1, comma, what do we get when we plug 1 into this function? That'd be 1 to the fourth minus 2 times 1 squared plus 2. That'll be 1 minus 2 is negative 1 plus 2, which is positive 1. And we will have the point negative 1, comma, 1 as well after we plug negative 1 in. And let's check real quick and see by the graph if these really are points where we have horizontal tangency. Let's graph x to the fourth. Let's minus 2x to the second and plus 2. Let's go zoom decimal to get a nice view of this graph, and I am looking at the point 0, 2, 1, 1, and negative 1, 1. Here's 0, 2. I can see a horizontal tangent. Here's negative 1, 1. Yep, that looks like a horizontal tangent, and 1, 1 as well. And do note for a later lesson, those seem to be places where the graph changes direction. This is a minimum, that's a maximum, this is a minimum. So we're in good shape there, and we can pause for now and join me back in the next video.